All right, I also want to start off with thanking the conference organizers, RFG and AbGradCon, FameLab. They were all blast. I've learned a ton. I'm probably the only one here who hasn't started graduate school yet, but I'm probably not the only one who had a typo on their abstract. So my abstract on the top, it says University of Cincinnati. That's where I'll be starting at the end of August, and I'll be working with Kira and also her advisor, Andy Chaya. This work was done while I was a postbac at University of Oregon with my advisor then, now my mentor, Greg Ritalik, and my awesome colleague, undergrad, Brooklyn Goes, who did great petrographic work and a lot of petrological work on this study. I'm just presenting most of the stable isotope stuff, and so I did a kind of a small part of it. But I'm really grateful for a lot of her work. The other one is said implications, but no, I'm saying consequences, so a little bit different. Okay, for those of you who don't know what Snowball Earth is, or what it is, and that's none of you, right? Okay, so we're down in South Australia here, and this is where we're looking at our rocks. The Snowball Earth was, there's been a couple of them, supposedly. We're looking at the last and supposedly the greatest worldwide glaciation event. Some have proposed that it hard capped all the way to the equators on both the continents and the oceans. And we're here to tell a little bit different story. You've also heard it be termed the Marinoan glaciation. That's from the nearby Merino rocks, and those overlap with the Ediacaran. So we think that the Alatna glaciation fits better from the Alatna formation, which coincides with the end of the Cryogenian. As you can see, those line up, and preceding the Ediacaran, and then the following Cambrian. So here we are, we're at the Renilla Siltstone, South Australia, looking at an outcrop. Unfortunately, I didn't get to go do the field work, but Greg brought back some awesome samples. These have previously been interpreted as submarine methane seeps. And they were deposited within a paleo latitude of 12 degrees equator. Actually, let me go back real quick. I want to point out the Flinders Range up here. This was deposited in a higher paleo latitude, but it has really, really good glacial evidence. It's got diamictites, tillites, things like that really indicate strong glacial evidence. So we're reanalyzing these outcrops to see what they say. Basically, we're arguing, is it a submarine seep or is it a subaerial soil based on the isotopes that we obtained. So there's a couple stark differences between the two when you're looking at them. Paleosols have a really indicative red color. Nodules are usually of a regular shape. They're not a nice circular form. And they have a little bit different composition compared to, you can see the methane seep type outcrop here, which has a gray color, smooth, rounded nodules, and a clay host rock. So a little bit different there. For all my strat people, there's your strat column. So this is what Greg brought back as a sketch, and Brooklyn had to put into a computer program to make it look nice and pretty like that. So you can see here these some of these interstratal deformation, where in a really developed soil, which I'm going to tell you there's soil, you can see it's really a elongate shape. And that's a little bit different, too, than what you'd see in a methane seep. Methane seeps are usually more tubular, so straight down kind of like that. And these kind of come in at a little bit of an angle like this, which is more indicative of a subaerial environment where these cap sands that are coming in and filling in are from a fluvial glacial type outwash. So you can see these large sand wedges and large nodules. The bigger it gets, the more nodules you get, the larger the duration of development before something happens. So this is a better kind of a representation of that. So you can see when it starts off, there's nice planar bedding, and as you get more developed, you see this nodules start to develop in place. That's what replaces means. And you can see as development gets more and more, you can see these structures come about. Don't worry about the names. Those come from some crazy Aboriginal language, and there's about 4 or 5 different Paleosol classification types, so I wouldn't worry too much about those. Now here's the nitty-gritty. I don't have any complex mathematical models or any crazy instrumentation, if you want to come see my mass spec, you can come up to me after. I'll give you a really sweet instruction manual. So here's what we're looking at, the stable isotopes we collected, compared to a previous study of that by Kennedy et al. In 2008. Now this sedimentary carbonate is from an unknown stratigraphic level, but we can see that it's definitely depleted in delta 18 oxygen. So for methane seeps, you usually get this really nice vertical cross plot that's associated right around 0. That comes from a couple of things. Usually it's because these are marine. So this is taken from a Miocene methane seep, but it's really well documented. So this is what we're basing it off of. And they had good isotope values. So we like to look at this and kind of compare the two. You can obviously see a stark difference in that between this nice linear covariance right here. That lines up with more recent soils, well documented in their isotopes as well. And they show this nice vertical cross plot. I'll come back to this in a second. So the implications of these, or let me explain them first, I guess, is you can see that correlation between the two, right? And that covariance is really unique to a subaerial environment. What happens there is that evaporative and biological processes select for mass of both isotopes in carbon dioxide. So that doesn't usually happen when you're in a marine environment where the oxygen content is dominated by the water. And so when you're looking at this, that's what you're seeing. The oxygen content is totally indicated by the water right here. And the variation in the carbon is from methanogenesis. So you can get depleted carbonate in that form, or from just from the methane seeps themselves creating the methane. This is really similar to what you're going to see. It's a really weird term, but that's basically saying it's similar to what you're going to see in a wetland environment. And that covariance right there, as far as we know, is not present in any marine rocks or sediments, so it's very indicative of a subaerial environment. This is a kind of hypothetical reconstruction. We're looking at maybe coastal plains, intertidal flats, yet still a very cold and arid environment. So it's not to say that during this supposed snowball Earth that we were in a temperate tropics. No, we were actually in a really frigid environment. It looked something more like the soils of Antarctica. It really is what it looked like. So cold, but we don't think they were glaciated. So this was definitely frigid, looking something like this. It's called pattern ground is what most people will call it. This is from a dry valley in Antarctica, and that's similar to the type of environment we're looking at. And where the cap sands are coming in and filled from this glacial outwash. In ice wedges, they're another type of similar form, but they form horizontal layers within the elongate area, whereas cap sands, they come in, and sand wedges, they come in and they fill almost vertically, or kind of in a awkward kind of fashion, irregular fashion, I should say. So these have no glacial tillites. As far as we can see, there's no methane seeps or extensive marine deposits. So we're not the first ones to say this. This was previously interpreted a long time ago, and we basically agree with the previous interpretation. The other thing is that it doesn't appear that this deglaciation happened immediately really fast, as has been previously proposed, when you had large amounts of methane going into the atmosphere to turn back and rebuttal this Snowball Earth event. It actually seems that the Ediacaran was rather cold too, and it took some time to get out of this, rather usually, geologically speaking, pretty normal. Now, let's get to the astrobiology. What does this mean for life and things like that? So this glaciation, which still was probably one of the greatest glaciation events the Earth has ever seen, it preceded the Ediacaran and the following Cambrian explosion, two big biological events in Earth's history. So we know this would probably play a huge role in how that proceeded. But how would photosynthetic life survive in an environment where you had the oceans hard cap all the way to equators, and how would Earth rebound from that? It's almost like the opposite of Venus, where it's a runaway icehouse effect instead of a runaway greenhouse effect. There's been a couple of things proposed: Snowball Earth model, thin ice model. Chris McKay is famous for that one, or well known for that one. And those are both definitely plausible too, but in our eyes, it seems that there was probably more likely an equatorial ocean, which climate models have also agreed with. So that's basically the simplest interpretation that we can come to with the data we've obtained. The good thing is life did survive and responded well. Thank goodness we can all be here. So this is what you could see some maybe previous interpretations thinking Snowball Earth looked like. This is what we think it looked like. Or maybe a little something more like this. So I'll leave you with that. Let me know if you have any questions. Thanks.
Hi, I was wondering if you could use water carbonate oxygen isotope fractionation to estimate the temperatures.
Water, say it again?
Water carbonate oxygen isotope fractionation.
To determine what?
The temperature.
Oh, to determine
formation.
temperature. Yeah, that's definitely possible. It wasn't part of our study, but it could definitely be done as far as I know. There's no reason it couldn't be, as long as you could get a representative outcrop and a good sample that could tell you that. I'm not sure. I mean, there may be studies already out there in indicating temperatures, but when you're trying to apply that on a global scale, it makes it a little bit tough. You know what I mean? You have to have a lot of decently supportive evidence and evidence that lines up. But it's definitely possible.
All right. Any more questions? All right.
Yeah, so looking at your the delta O versus delta C figure, all those other data points are the same rocks in the same region?
These?
Yeah, so Arizona, okay.
So yeah, you can see some of these are quaternary, so they're
Okay.
actually really young.
Yeah,
But
very
but
young.
they still have that stable isotope covariance there. These were taken. So the red ones were the ones that I studied in particular. And in the Kennedy paper, he actually has some carbonate values too that actually line up a lot better with this one. I'm not sure why we didn't include them in the figure. But yeah, they were taken from a lot of different places, and what this basically indicates is the more your Paleosol gets developed, the more depletion and covariance you're going to develop.
Right, so I guess what I'm curious about then is whether or not these rocks and other rocks of the same age and similar rocks have been studied anywhere else on the planet besides just this one region to find out if these are Paleosols similarly.
Well, as far as I know, these are Paleosols. I always tell people a lot of people study marine science for a lot of good reasons. Not a lot of people study Paleosols, also for a lot of good reasons. So they're not well preserved in the rock record, you know what I mean? So you have to be really careful about when you find them and when you interpret them. And if there was only a thin section, 12 degrees, 15 degrees paleolatitude where there was actually Paleosols there, everything else was covered by glaciers. So if you could find more evidence from that time, Neoproterozoic, right time period, and find more Paleosols and corroborate that, then absolutely. It's just they're hard to find.
Thank you very much, Jeff.
All right, thank you.